All right, so welcome back. So today we're going to be talking about significant figures. So you may have watched this or watching this right after you did scientific notation or right before scientific notation. When it came to developing this unit, I thought they could be interchangeable. So if there's a couple of things you don't understand in regards to scientific notation, don't worry, we'll get into that. Or if you need to refresh it, go watch that video. Otherwise, you may be familiar with it already. So no worries, we're just going to kind of dive right in here. So the importance of significant figures. In science or in the scientific community, significant figures are used to determine how precise a measurement is. So these significant figures are determined by the data or the experiment that a scientist does, and we use that to help validate our conclusions or hypotheses that we may come across. In a significant value, all designated significant digits are accounted for, as well as one estimated digit. So there are some digits that will not change, that are determined by the parameters of the experiment, and then there's typically one at the very end that helps determine a rounding significance to our data. And so we'll kind of dive further into that later on in this video. But the nice thing is the same rules for significant digits are used all over the world, so that scientists have the best ability and data to rely on when duplicating somebody's work. So it's very important for scientists, like for example in Asia, if they wanted to try to create a new element and they have data for it, their significant digits may be based on their scientific technique as well as their equipment that's used. So if their significant digits are not right, when people across the world, like in USA, try to duplicate their experiment to validate their conclusions and hypotheses, if the data comes out wrong, that might, not have them win a Nobel Prize. So it's a very important thing, but very simple rules to follow, and you'll definitely get with definitely a bit of practice. So there's a couple rules of significant figures. So what I'm going to do is I'm going to break these rules into parts, and I'll do a couple of examples for each rule, and towards the end we'll start compiling all these rules together to kind of make a little bit more sense. So the first one is that all non-zero digits are always significant. So we'll explore this a little bit. So how many significant figures, or what I will call sig figs, you'll hear that a lot probably as I'm talking to you in class because that's just how I've learned it, but sig figs are in the following numbers. So what we have to ask ourselves is that how many non-zero digits are in this number? Well, there's 3 digits and they're all non-zero, so therefore there are 3 sig figs, or significant figures. Same thing here. There is 4 digits, all of them being non-zero, and that means that there's 4 significant figures here as well. Now this one, even though it is a decimal, the decimal itself does not matter. It's just a placeholder. It's supposed to demonstrate if the number is really small or not. Just decimals do come into importance when it comes to scientific notation, but in regards to significant figures, not that much. So all 3 digits that are demonstrated here are non-zero, so therefore all digits are significant figures, and there's 3 sig figs. So second rule is all zeros between significant figures are always significant. So again, take a number like 1001. Well, we know from the first rule that the first digit, if I can get my mouse to work, okay, is the first digit here is non-zero, so it's significant. The last digit here is non-zero, so therefore it's significant. So these 2 zeros are in between 2 significant digits, or significant figures. So therefore those 2 zeros are also significant. So you tally them up and you have a total of 4 sig figs. Same thing, so all non-zeros are considered significant, so 2 and 4 are significant, zeros in between it. Therefore, all 4 of these are significant, and you get 4 sig figs. Now this one's a little bit more tricky. So the thing is that obviously 3 and 5 are significant, but there's no significant figure on the other side of the 0. So therefore, these 3 zeros are just what's called placeholders. And so since there's not another significant figure over here, they're not in between 2 significant figures. So there's only 2 sig figs in this number. So 3 and 5 are significant, the other 3 zeros are not. So the third rule is that all final zeros to the right of the decimal are significant. Sometimes, most of the time, these might be the estimating digits, but they are significant in this sense. So if I was to look at 20.0, we know that 2 is significant because it's non-zero. We know from this rule that the third, I don't know why my mouse is not working, there we go. We know that the 0 to the right is significant based off this rule. So therefore this 0, since it's in between 2 significant digits, is also significant. Therefore 3 significant figures. This one also 3 and 5 are significant because they're non-zero. The last one to the right is also significant. Okay, so the right of the decimal is significant, but all of these, since they're in there, they're also considered significant because they're between the 5 and the 0. So there's 9 sig figs. You typically won't see this. Typically won't see 9 sig figs. I mean, it can be a thing, but mostly we'll denote this in scientific notation to get rid of this large number. Now this one's a little bit tricky, so we know that the 1 here is significant because it's non-zero, but the decimal here is right here. There's no 0 to the next of it, so there's no significant digit on this side. Therefore, all of these are placeholders. So there's actually only one significant figure in this whole number. Now, the number of significant figures may change if you use scientific notation, which we can kind of explore in the next video. All zeros that act as placeholders are not significant. So again, same question. I have 100. Well, we know that 1 is significant, but there's the decimal's right here. There's no 0 to the right. So therefore, these two are just placeholders. So there's only one significant figure. Same thing here. 2 is significant because it's non-zero. There's no 0 to the right of the decimal. Therefore, there's not a significant digit on this side. Therefore, all of these are also placeholders, and they're not significant. Now this one, there's a 3 and a 5. They're both significant digits. Therefore, according to the second rule, the zeros in between the significant digits are significant. So all of these digits are significant, which brings it up to 5 sig figs. Now this one's a little bit more confusing for our students. It's all counting or exact numbers and constants have an infinite number of significant figures. They're also called conversion factors, which you may have heard of from middle school or in your physics class when you were doing dimensional analysis. Pretty much what it means is that conversion factors are precise conversions or measurements that have already been made. They're accepted literature values that their significance has already been determined. Therefore, there's not really any part of those significant figures that you have to really worry about when you're writing a constant or number. You just really write the given value, their literature value, and when you do your calculations with those, based off your calculations, the final answer, your significant figures may change. We'll get more into that later, but just the constants and the numbers by themselves, they have an infinite number of significant figures. So for example, 1 hour, 1.0000000, etc., infinite zeros is what this says, equals 60.00000 blah, okay, minutes. Okay, so they have infinite significant figures. We just write it as 1 hour and 60 minutes because those zeros we don't care about. Okay, so we don't care about those significant figures in this case, but they can be significant because we've gotten that measurement down to such a precise number. Same thing with 12 inches in 1 foot, or 365.250000, etc. days for every 1.000, etc. years. So rules of rounding. This is a little bit tricky for some, but this is based off the estimating digit, which we'll get to here in just a second. But pretty much there's a rule that we say is that if it's 4 or below, you keep it low. If it's 5 or above, give it a shove. Okay, shove it up. But in this one, so the rules of rounding is if the digit to the right of the last significant figure, which is the estimating digit, is less than 5, you do not round up. If the digit to the right of the last significant figure is more than 5, then you round up. Okay. Now it can get a little tricky with rounding. There's been disputes on how rounding occurs, on where you round and everything, but I want to teach you the way I've learned through high school and college. I think it's the way to go, but we'll go based off of that. So here we go. So when it comes to a couple of examples, let's take a look at this. If I was to round 535.28 to 4 significant figures, what would the resulting number be? Well, you have to determine where your last significant figure is and your estimating digit is. So we know all these are non-zero numbers, so we know they're all significant, but I only want 4 of them. So I go 1, 2, 3, 4. So 2 is my last significant figure. 8 is therefore my estimating digit. So if 8 is above 5, I'm going to give it a shove. So this is going to round it up to 535.3. Now take a second to see if you can do this one on your own. Alright, so when it comes to this one, we want 3 significant figures. Well, the 0 here, since it's in front of the decimal to the left, this is going to sound a little weird, it's significant because that 0 right there matters. Okay, you can't have, I know a lot of times in math you put just 0.0 something, Okay, but in science, you have to have the 0 in front of the decimal, so it's considered significant in this case. So 0.0134, we only want 3 sig figs. Well, since the 1 is non-zero and this is considered significant, that means this 0 is considered significant. So we only want these first 3 digits. So that means 3 is our estimating digit. Now there is this 4 next to it, which would be the estimating digit for the estimating digit. So if you really wanted to do it, 4 is lower than 5, so you're not going to shove 3 up, which means 3 is lower than 5, and you're not going to shove 1 up. So therefore, it's going to be 0.01. So at this point, we're going to do a little extra practice. If you're really comfortable with this, feel free. You can skip this part. However, I do recommend going through this with me. If you have any questions, feel free to come see me or revisit this video later. But I'm going to go ahead and try to bust through these as soon as possible here for you. So we're going to round all the following numbers to the 3 significant figures. So the first one is we need to look at how many significant figures we have. Well, all 4 of them are significant because they're all non-zero, which means that we want to be left with just 3, which means we only want 2, 3, and 4, these numbers right here, which means this is going to have to become insignificant somehow. How do we do that? Well, we got to get it to round to 0. So what we do is that we say, okay, 4 is our last significant digit that we really want to worry about. 7 is our estimator. So 7 is greater than 5, so you give 4 a shove, and it turns into 2350. So 1, 2, 3 significant figures. This one doesn't matter because it's just a placeholder. This one, again, we want to go 3 significant figures. So this 0 does count. This 2 is also a significant figure, which means this 0 is a significant figure because it's in between these 2. So we want just these 3. So that means 5 is my estimating digit. Well, you got to kind of estimate from the bottom too. Does 4 give 7 a shove? No. But does 7 give 6 a shove? Yes. And that means that's resulting 7. Does it give 5 a shove? Yes. So therefore 6, which this will turn into, does it give 2 a shove? Yes. So that estimates to be 0.03. Now, this one is in scientific notation. Don't worry, if you haven't seen scientific notation yet, we'll explore it in the other video. But when it comes to scientific notation, you don't have to worry about the exponent. I do not know why my mouse is not working. There we go. So the exponent does not matter here. We just have to focus on this number. So it also wants 3 significant figures. So 3.004, this is significant, which means these 2 are significant. We only want the 3.00 placeholders right here. So we got to see if this rounds up. Well, estimating digits, does 7 boost up 6? Yes. Is 7 greater than 5? Yes. So we boost this up. And is 5 greater than 5 or as 5? Yes. So 5, you boost it up. So this turns into 3.01 times 10 to the 5th. So it's like it barely made it, but it's like right there. Now, whoops. A lot of people may disagree with that. The rounding rules have changed, but I would not, I would probably take both answers if need be, but that is how I round, how I believe is the proper way to round. Some other teachers may disagree with me, but that's what I learned in my college experience, so that's what I'm going with. But if you have any other questions, concerns, feel free to email me, come talk to me. Rewatch this video if you need to for extra practice. Go visit the scientific notation or revisit this video if you need to, and vice versa. Thanks for joining me, and I hope to see you in the next video, and see you soon in class. Bye.